All right, last time we talked about collisions. I mentioned 3 types of collisions. All right, so let's go ahead, put those down. We have elastic, inelastic, and perfectly inelastic. I kind of move this one over because this is just a specific example of inelastic. Okay, elastic, delta E is 0. So when I tell you that a collision is elastic, immediately you know that energy is conserved. Usually, and it's rarely ever not the case, but usually, delta PE is equal to 0, and therefore delta KE equals 0, and therefore the kinetic energy is also conserved. Okay. Now, this could be violated if you have something on, there's 2 objects on an incline colliding. I will not be providing anything like that. So everything will be taking place on the horizontal. Inelastic is the opposite. In this case here, delta E does not equal 0. And therefore, you do lose energy in the collision. You lose energy to the surroundings. And I'll explain here in a moment what I mean by that. The energy of the system itself, though, that you're examining, if it's undergoing an inelastic collision, it loses energy. Okay. And then there's perfectly inelastic, which means that you lose the maximum amount of energy that's possible. And you can think of this as sticks together. Okay. So those are the 3 kinds of collisions. Let me show you what we mean by that. This is an elastic collision. Okay. This, and I'll keep in mind, what's the system? Both bodies. Okay. This system is undergoing an elastic collision, means that these 2 bodies in the system do not lose any energy during the process. Okay. Why don't they lose energy? Because, well, again, when is energy lost? Energy is not conserved, energy is lost. Energy is not conserved when there is a non-conservative force doing work. Well, the non-conservative forces here, well, there's only one. There is a normal force acting up, but it's always perpendicular to the displacement of the car. So the normal force acts on the body, it doesn't do any work on the body. Now you might think, well, what about the force of interaction between these 2? Actually, it's magnetic, and in this case here, it would be conservative. And that's something you'll learn in physics 2B, okay? So you can take the word for it that this type of collision here, where you have 2 magnets coming together here, is an elastic collision. Now, what about a inelastic collision? Well, inelastic collision is if I hit this thing hard enough, I can make it hit, listen. Try that again. You hear it? Not so much there. Hear it? Okay, what's happening? Now, these cars are moving so fast that they actually come in physical contact with each other. And when they encounter and hit each other physically, they impart forces on each other, and these forces are non-conservative. Okay, so there's energy lost. You can tell there's energy lost because you can hear it. Sound is a form of energy. It's a form of kinetic energy. And the fact that you're hearing it means that the sound is emanating away from the system towards you, so it's dissipating out. And therefore, the system itself is losing energy to its surroundings. In this case, the sound emanating from the objects. Okay, so that's inelastic. Now, what does a perfectly inelastic look like? Well, I said it sticks together. So let me go ahead and see here. I think I can turn these around and make it work. Yeah, so So here's an example. Oh, no, that's not an example. Bad. Trying to get. Oh, that's not that. Okay. So here's an example of a perfectly inelastic collision. They stick together. Okay. Energy is lost. In fact, the maximum amount of energy that you could lose in a collision is represented by this type of collision where the objects stick together, and that's called perfectly inelastic. All right. So that's the definitions. So I thought I would set up the really hard, not the hardest, but one of the more general momentum conservation problems. Show you how to set it up. I'll let you do the math on your own if you wish. But you need to know how to set up the problem. So let's see here. All right. Where'd my squirt go? And we're going to do a elastic collision. Okay, so this collision, it's elastic. And let me model it for you. We're going to do this problem here. Where the two objects are coming together and bouncing off each other like this. Of course, they can't hit each other. If they hit each other, it becomes inelastic. And what would be the question? Well, for example, suppose that I knew the speeds, I was able to measure the speeds, and I wanted to know the masses involved. Okay, so I know, I should say I know the velocities. I know the velocities of each of these objects before and after. I can measure that by looking at them. And I'm kind of curious as to what their masses are. Could we solve that? Okay. Now, being elastic, immediately you should know that energy is going to be conserved. And since this is all on a horizontal plane, that means that kinetic energy is going to be conserved as well. Also, by looking at this, you can tell, because this is all flat, that momentum is conserved. Why? If the momentum is conserved of the system if both bodies are the system. Okay. And why? Because the normal force and gravity forces cancel, and the forces between these two bodies are not external, they're internal. They're not forces that act on the system, and therefore they don't count. And so there's no net force acting on the system, momentum is conserved as well. All right, now, the question now is, how do we solve this? So let's go ahead and put down, we have a mass M1, and it's traveling at V1 initial in this direction. We have M2, and it's traveling at V2 in this direction. And they collide. Blammo. After they collide, M2 is probably going to be going back in the other direction, which is what happened when we launched it. We'll have to call this V2 final. And this one is going to have to be going in the other direction. Well, it doesn't have to, but that's what happened. V1 final. Okay. Now, let's go ahead and put in some values here. We'll say that this is going at 4 meters per second. This will be going at 3. And when they bounce off each other, this one's going backwards at 6, and this one's going at 2. And of course, these are meters per second. Those are the speeds that the objects are moving. How do we solve this? Well, first of all, we're going to conserve momentum. And when we conserve momentum, We've already established that momentum is conserved. Therefore, delta P is 0. That means that the total potential energy before is equal to the total potential energy after of what? The system, both bodies. So we could go ahead and do that. We end up with what? M1 times 4 this is P1 initial plus M2 times -3. So this is the total momentum before. And by the way, I just underlined this is not underlined. This must equal to the momentum after, which is going to be M1 times -6 plus M2 times +2. Okay, so we can clean this thing up a little bit. I'll write it over here. 4M1 minus 3M2 is equal to, I'll put the last one first, 2M2 minus 6M1. Momentum conservation is very simple. Now notice, momentum is a vector. You have to put in the proper signs, plus or minus. You can't remove the arrows off the top until you do. So now let's do kinetic energy. Energy, but remember we said that kinetic energy is also conserved here. And what's the energy of this system before? Well, it's the energy of both of these bodies. In this case here, we would have the kinetic energy of this one. Oh, by the way, remember, I forgot to write this down, I'm sorry. Momentum is equal to mv, and kinetic energy is 1/2 mv squared. So the kinetic energy of this body is what? 1/2 times m1 times the speed squared plus 1/2 times this mass times this speed squared. You're thinking, well, why is it at -3? Kinetic energy is a scalar quantity. It's always positive. You can put a -3 there you want, but you're going to square it. It's about to +9 anyway. And that's got to equal what? 1/2 times m1 times speed squared plus 1/2 times m2 times the speed of this one. Squared. The nice thing is here is that the 1/2s all cancel. Every term's got a 1/2, so I can just come through here. This. I could write this as 16m1 plus 9m2 is equal to 36m1 plus 4m2. And I end up with 2 equations and 2 unknowns. I will then solve that on your end. Remember, the ability to solve simultaneous equations is a prerequisite for this course. So there are plenty of online tutorials that can show you how to do this. So anyway, this is the elastic collision. Okay, where are the mistakes made? The most common mistake is putting negatives in front of the kinetic energies, depending on the direction of the arrows. Kinetic energy is a scalar, it's always positive. Also, forgetting to square the velocities is pretty common as well. So, that's something to watch out for. All right, I want to talk about one more type of collision that you might encounter in your homework. And by the way, it's quite possible to create a system here that has no solution because the speeds aren't right. So if you get something really goofy going on, that's what happened. So I wouldn't worry about it. What I mostly would worry about is make sure you understand how I set these 2 equations up. The next thing I'm going to talk about is the explosion. And this is a perfect example here. So what I can have are, like, for example, it's quite common to have chemical compounds. These chemical compounds can store a lot of potential energy amongst them. And so these molecules are placed in proximity to each other, and they have a lot of stored potential energy between them. What happens if I can release that energy? It's the same thing as when I let go. They split apart. Okay. Why does that happen? Well, sometimes it could be because you raise the temperature of the molecules. They tend to oscillate, vibrate because of that, and then they can break their chemical bonds. And at that point, you can have them actually start to release each other. There's all kinds of interesting chemical things that could go on, but it's really more in the realm of chemistry. So at any rate, you have lots of stored energy. And then when you release that energy, it goes into kinetic energy. So you have potential energy, which we can also call chemical potential energy. Remember that we had gravitational potential energy, and we also had spring potential, and now we have chemical potential energy, which is very closely related to the spring potential. So you can think of these molecules as sort of like being compressed by springs. And then that chemical potential energy is converted to kinetic energy. Okay. So how do we solve this problem? So before, we have both bodies at rest. We'll call this M1, M2, and they have a lot of potential energy stored amongst them, okay, and they're at rest. After we ignite them, and this could be like pulling a pin on a grenade, it could be lighting a fuse, it could be triggered by a lot of things. We ignite them, we have an explosion, and M2 will travel to the right at some speed V2, we'll call it, and then V1, N1, sorry, will travel to the left at some speed V1. Now, the question becomes, is potential energy, is kinetic energy? We won't worry about potential. Are they conserved? Well, let's make it a little, let's back up. Let's say, is momentum conserved? One step at a time. The answer is yes. We do have, each one of these has a normal force acting on it and gravity. But these forces cancel. There's no acceleration up or down. This body applies a force to this one. Newton's third law says that this body must apply a force to this one. But those forces are internal to the system because we define the system as both bodies. Therefore, all the forces acting on the system vector cancel, momentum is conserved. So we're going to write that down. Momentum is conserved. What about energy? The answer is no. The reason why energy of the system, and I have to be kind of careful here, we're not talking about the energy of the universe. We're talking about the energy just of these bodies here. Their potential energy and kinetic energy, that energy is not conserved. And why? Well, if you ran this thing backwards in time, what would you see? You'd see these two bodies come and stick together. That's perfectly inelastic. That's the maximum amount of energy lost. This is just the perfectly inelastic collision run backwards. So this is a perfectly inelastic collision. So energy is not conserved. And when energy is not conserved, your job usually gets a lot easier because you don't end up having to do a lot of the squares and stuff like that. But momentum is conserved, energy is not. So all we can do is conserve momentum. Well, we have to say that because because momentum is conserved, momentum initial must be equal to the momentum final. But the momentum initial here is 0. Right. Initially, these bodies weren't moving. So after momentum final, we get what? M1 times V1, but V1 is V1 points in the left-hand direction. So this is going to be M1 times it by negative V1. I took the arrow off the top by sticking the negative sign in there. Now V1 is just speed. Plus M2 times V2, and this direction is positive. V2 points in the positive direction. And this, according to momentum conservation, so 0 is equal to, I'll switch the order here. So this will be M2, V2 minus M1, V1. And then I can bring this to this side, and I get M1, V1 is M2, V2. Therefore, if I know 3 of these, I can calculate the 4th. The perfectly inelastic collision is really simple to solve. Okay, so I think you have a web-assigned problem involving a bullet. This is how this one's done. Okay. The bullet and the rifle are together motionless, so the momentum total is 0. Afterwards, you got the rifle going in one direction, you got the bullet going the other direction, and those momentum must vector sum to 0 because the initial momentum was 0. So that's the explosion. Make sure you know how to do this problem. Okay. By the way, put some numbers into the examples I'm doing for you, work it out. Okay. All righty. The next thing we're going to do is one of the coolest physics demonstrations around. I mean, it's not exciting. It's pretty cool. Hang on. This is called a ballistic pendulum. And it's a model of what they used to use back in the old days to measure the muzzle velocity of bullets. Back in the old days, you didn't have high-speed cameras or lasers or like that. You had to find ways to figure out how fast a bullet is traveling when it leaves the barrel of the gun. And this was how it was done. Okay, so what we have is a bullet. We're going to load it into our gun. Actually, where did it go? Oh, 1 second. Okay. And what's going to happen is that when I fire this gun, the bullet's going to come out and land into my little block here. The block will absorb it. And this block will rise up to some maximum angle. Watch. Stick in there. Hang on, let me try that again. Stay in there. Let me put on a very slight incline. That way the bullet stays in the back. Let's see here. Work. That might help. It's clear. It's supposed to land inside, and this comes up to some maximum height. But for some reason, the bullet is coming out, and I don't know why. Not supposed to do that. I've done this thing a million times, but there are some adjustments that have to be made on it. You can see the little sliders, and I don't want to take the time, but that takes a while. So at any rate, I'm going to model it on the actual board here about what's going on. Okay, so what we have is a block. It's usually a block of wood that's hanging from a string. And a bullet comes through at high speed, embeds into the block, so that afterwards, the block rises to some maximum angle. Now, we're going to use, instead of a maximum angle, okay, so here's the bullet in the block, and we'll call this height H. Okay, so you see, comes in, thump, rises up. And the question now is, if I know the mass of the block and the mass of the bullet, and its height, how fast was the bullet traveling when it hit the block? Okay, the ballistic pendulum is a really cool problem. It's easy to solve if you take this in two phases. There's going to be two phases. One is the collision. The bullet embeds into the block. Phase two is the, we might call this trajectory. The block and bullet rise up to some maximum height. So thump, phase one, and phase two. And we now have to ask ourselves, what's conserved in phase one? What's conserved in phase two? And by that, I mean, is delta P, so let's say phase one here, is delta P conserved? Is delta energy conserved? Say, is momentum conserved? Is energy conserved? Phase two is momentum conserved? Is energy conserved? You should turn off your YouTube video right now and try to answer these two questions. Now, keep in mind something. So, yes, there are tests that we apply to determine whether momentum is conserved and energy is conserved. Go back to the tests. Under what conditions are these conserved? Does the system satisfy those conditions? Okay, so turn off your YouTube video, think hard, go back through your notes, go back to where we define when momentum is conserved and when energy is conserved, and see if what's happening there. And see if you can answer these questions. Okay, so I'm going to assume now you've had plenty of time to think it over. You might give it up. Or you have got the answers that are wrong, because almost nobody gets this right. Because why? They don't go back to the original tests. They try to figure it out. Okay. Momentum is conserved. Let's see, phase one is this phase here. Momentum is conserved when there are no net external forces acting on the system. We have a bullet hitting our mass and embedding into it. Okay. What are the forces acting on our system? Well, we have mg, and we have tension. The block exerts a force on the bullet, and the bullet exerts a force on the block. But if our system is both bodies, bullet and block, these two are internal. Now, F of t and mg vector cancel. Therefore, momentum is conserved. So yes. What about, I'm just going to verbalize this part. What about energy? No. It's perfectly an elastic collision. The bullet is sticking to the block. The force that this bullet applies to the block and the block applies to the bullet are non-conservative. And therefore, and they do work on each other. Energy is not conserved. Perfectly inelastic collision. Not only is energy not conserved, but the maximum amount of energy that can be lost is lost. Where does the energy go? Heat, the energy goes to the surrounding block and heats it up and then heats up the air around it. Also sound. The bullet actually makes a sound when it hits a block, and that's also lost energy. What about phase two? Momentum is momentum conserved? No. Why? Well, first of all, you can look at it and tell momentum is a vector. This object is changing direction. The velocity vector is changing direction. The momentum must be changing direction. And if you have a change in the direction of the momentum, it's changing. So just by looking at this thing, you know momentum is not conserved. Furthermore, the velocity goes to zero, and therefore the momentum goes to zero, and therefore momentum can't be conserved. But let's take a look at the test case. What are the forces acting on our system? We have gravity, and we have tension. But these two they don't vector cancel. The vector cancel, they'd have to be equal and opposite. Since there's only two forces. But they're not. In fact, there is a net force in this direction. Parallelogram method. Therefore, because there's a net force acting on the system, momentum is not conserved. Is energy conserved? Yes. Why? Well, what are the forces that act on the system? Well, we already have them up here. Right? Force of gravity is conservative, and the tension force is non-conservative. However, there is a non-conservative force acting on the system, but notice something, that this tension force is always perpendicular to the displacement. Whatever direction the object is moving, whatever displacement it undergoes, I should be more careful. Whatever displacement undergoes, it's perpendicular to the tension force. So the tension force acts on the system, but it doesn't do any work on the system. Therefore, there are no non-conservative forces acting on the system. Energy is conserved. So in phase one, we conserve momentum. Phase two, we conserve energy. In phase one, what's the momentum look like? Well, P initial is what? Just the momentum of the bullet. I'll call it VB. Right? Because this block isn't moving initially. After the bullet embeds, it's going to be moving. The bullet and the block are going to be moving initially at some speed that we will call V prime. Right at the moment that the bullet embeds into the block, both of them are going to move at some initial speed V prime. We don't know what V prime is, but we know it's there. So after the collision, P final is the combined mass, big M plus M sub B times V prime. And notice V prime and VB both point to the right, they're both positive. And momentum conserved means that these must equal each other. So MB, V sub B must be equal to big M plus M sub B times V prime. Now, quite often in these calculations, they leave the MB off because big M is so much bigger than MB that it doesn't, that for all practical purposes, you can just call this big M. I typically don't. I leave it in there. Now, what about later here? What about here? Well, in this case here, delta E is 0. And when delta E is 0, we end up with, first of all, what's the energy before? The energy before is this combined mass moving at V prime, kinetic energy. So the energy before, energy initial, is 1/2 times M plus MV, V prime squared. What's the energy after? Well, when this thing comes up to its maximum height, it comes to rest momentarily. It might swing back down, we don't care. So it comes up momentarily to rest. The only energy, therefore, it has is potential energy, mgh, gravitational. So the energy final is M plus M sub B G H. Energy is conserved means that this is equal to that. And notice when I said this equal to that, the masses cancel. That makes it nice. So what I'll get is 1/2 V prime squared is G H. And now I can find V prime. Multiply both sides by 2. Take the square root of V prime. And then I can substitute V prime and solve for VB. So projectile, I'm sorry, the ballistic pendulum is a very sweet problem because it really makes you go back and think about when is momentum conserved, when is energy conserved. Also, I like these little two-phase problems. They're a little bit more interesting, I think. So know how to do the ballistic, won't be for this exam 2, but for the final exam, this is fair game. And I do like the ballistic pendulum. Make sure you know how to do this. There are plenty of YouTube videos on this. I'll post some videos probably over the weekend. Okay, that's all I have for today. Till next time.